Hi, I'm Shah, and here is my video on Lab 1 constant velocity. The objective of the lab is to observe an object that is moving at the same speed without direction change, making a computational model to predict that in ideal circumstances, and comparing the two. The physics concepts used in the lab are the Newton's second law, which is F equals ma, that is force equals mass times acceleration. Other equations used in the lab are the velocity change and position change equations. The velocity change equation tells us that the change in velocity equals acceleration multiplied by time the acceleration is applied. The position change equation tells us that the change in position equals velocity of the object multiplied by the time it is in motion. To create an experiment that follows the objective of the lab, my group used a small weight and lodged it between 2 meter sticks and rolled it from the 0 mark to the 1 meter mark, ensuring that the only force applied to the weight was at the start. Here is a video of the result.
Go ahead.
Then I used the tracker software and calibrated it to the length of the meter stick and tracked the position of the weight as it rolled along the length of the meter stick. The start and the few subsequent frames after the start of the video were omitted from tracking because the weight was still speeding up due to the initial force. Some of the end of the video is also omitted. The data derived from this shows that the relationship between the time and the track velocity. And when that is plotted on a graph, it shows that the y velocity starts off high at around 0.544 meters per second, but then slowly tapers to 0.392 meters per second. In the computational model, the initial velocity is taken as 0.544 meters per second to match the observed version, and the same time is used. The F equals ma equation is used to calculate the y acceleration on the weight, which is calculated to be 0 since no other forces are applied on the weight during the observed time. The acceleration is applied to the velocity change equation of vy final equals vy initial plus acceleration y times time, which shows us that the y velocity remains constant throughout the entire duration of motion. This leads to into the position change equation, which is y final equals y initial plus y velocity times time. The values are computed and the final data is obtained. When the two sets of the data points from the observed experiment and the computed experiment are compared in Excel, you can see that unlike the computed model where the velocity stays constant, the velocity in the observed function fluctuates and reduces over time. When the positions are compared, the observed data points plot kind of a curved point, whereas the computed data points plot a straight line. The reason for the discrepancy in computed data versus observed data is because we do not consider frictional forces in the observed data, which provides a negative acceleration on the weight that reduces the velocity or the duration of its motion, and therefore deviates it from the computed data. What if question? So if in our scenario I switch the plus y-axis with the minus y-axis and inverted it, then the data itself will remain the same, but the sign of the values of the weight's position and its velocity would change from positive to negative, and the graph that would be plotted would kind of show a negative graph. What does it mean? Question. Is it possible for me to say how many pushes or pulls were added to give the zero net force? And I would probably say yes, because the number of forces acting on the weight can be calculated. Initially, it was just the position on the system due to us pushing the weight forward. After that, since we are presuming ideal conditions, no other force in the surrounding, which is the table, are being applied on it. Upward contact forces like the normal force cancel out with gravity, ensuring that the net force on the weight is 0. Thank you.